this is a quick summary of the lesson Temperature of Stars, taught at Edexcel College in Malaysia with my Year 13 physicists. So the aim of this lesson was to understand how stars vary with temperature and to start looking at spectral class. Actually, in this lesson we didn't get on to that, so that will be covered in the next video. What you need to be able to do for your A-level is use the Stefan-Boltzmann's law and also Wein's law as well. And then later on we'll look at how to apply this to find the spectral class of a star and look at how that changes over something's lifetime. I asked you to start off by thinking about why hot metal glows. Now, if you remember back to year 12, you'll remember that when something gains energy, electrons jump up to a higher energy level, and when they drop down to a lower energy level, they emit photons. And the bigger that energy difference, the higher the energy of the photon and the shorter the wavelength. You may also start to think that the more object we have, the more of those photons we're going to produce. Maybe this will be a point to pause the video, just have a think about that. Okay, so we started off by thinking about how the temperature of an object can affect the brightness of the light that it gives up. So this is an equation called the Stefan-Boltzmann law, and it tells us that the hotter an object is, the greater the amount of light it gives off. So this equation, we have L, which is represented as luminosity in watts, so that's the total amount of energy as light that's coming out. We have sigma, which is just a constant, and then it's related to the surface area of the star, and its temperature raised to the fourth power. Okay. That's okay. And there's the Stefan-Boltzmann constant. It's 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the power -4. So luminosity then is, as I said, the amount of light that we get out of a star every single second. And you can see that very, very important is the temperature of the star. If you double the temperature of the star, you get, the luminosity goes up by a power of 4. Similarly, the larger your star is, the greater your luminosity will become. So, we look at some stars in the night sky and they're all different brightnesses. So, does that mean that we can find their temperature? Well, no, it doesn't, because we don't know if they're just very, very bright or if they're far away. All we can see of a star is how bright it appears and its colour. Although these stars look large, that's just actually because they're bright and they're exposing more of the photo film in this picture. They're not actually appearing larger in the sky because stars are all so far away that they appear like point sources of light. So we're going to need to do something else. Well, fortunately, stars follow something called a black body radiation curve. And that's a theoretical curve, but it tells us the spread of a spectrum of light that a perfectly black object would give off at different temperatures. So on the left here you can see this theoretical curve, and it tells us that as an object gets hotter, we have different wavelengths of light given off. So you can see that for this particular curve, I have a very large amount of blue light given off. Now I can simulate that online, and there'll be a link in this video, where if I change the temperature, you can see that this peak intensity changes. So the Stefan-Boltzmann's law would actually tell us the integral of the area under here. That's the total energy. This is telling us the energy at a specific wavelength. So the Stefan-Boltzmann's law just tells us the total energy, but what you can see is as the temperature increases, where this peak energy, the most intense radiation is, actually changes wavelength. And that's quite handy for us. It starts to give us a lot of extra useful information. One thing to point out, stars don't follow a perfect black body curve because they're not black. They're different colours. But what you can see is, for two different stars, they do follow the same rough shape. They're a bit messier, but they follow the same rough shape. So, using lots of complicated equations that we're not going to go into, we can come up with something called Wein's law. And it is that the maximum wavelength times the temperature is always the same. It's always a constant. And we call that constant Wien's constant. So if you look here, I could use this peak wavelength here, about 520 nanometers, and work backwards to find the temperature of my star. So now can we find the distance of these stars? Well, what we could do... Hello? Okay, so is it going to be possible now to use Wien's law to find out what their temperature is, and then from their temperature, find their luminosity? Well, almost, but we do need to know how much light is actually being received and how that relates to distance. So, what we call the light received is the radiant energy flux, and it has a unit watts per meter squared. So it tells us how much energy is hitting 1 square meter. Now, to work out how to do that, we need to look at something called the inverse square law, and that tells us how light spreads out. Now, if light spreads out radially, that is in a sphere, it will spread out with 4 times the area every time the distance doubles. That means that force is proportional to the distance squared. Now, for light, that means that the flux is equal to the initial luminosity divided by the surface area of an imaginary shell. So we can imagine the light spreading out in a shell, and in that shell, all of that energy has spread. So that will give us the radiant flux density in watts per meter squared, and you should be able to see, do a bit of dimensional analysis, that this will give you meters squared. So it's watts per meter squared. Hooray, physics works. So can we now find a star's distance? Well, let's think about it. We could find the peak wavelength of the star's light and measure its total radiant flux density. That will tell us the luminosity of the star. Then we could we can measure a star's wavelength, and we can measure how much energy is actually reaching Earth. Those are the only 2 bits of information that we can get. But we can, from its blackbody distribution, from the most frequent wavelength, that will tell us the star's temperature. And from the star's temperature, we can then find its actual luminosity of where it is. So we now know how brightly it's shining, and we know how much energy is reaching us. So we can then use the inverse square law to find the distance of the star. Does this work? No, unfortunately. A couple of reasons for that. Number one, stars aren't perfect. They're annoyingly real world, so they don't emit perfect black bodies. So Wien's law doesn't actually work. It gives us a good approximation, but it's not precise. The second thing is, we don't know how big our star is. Stefan-Boltzmann constant, if you remember, L is equal to sigma times A times T to the power 4, but we don't know what A is. So the only way this method works is if we assume that all stars are the same size as the Sun. And as we'll find out in the next lesson, no, this A changes. So in the next lecture, we're going to talk about what we need to know about how a star's brightness and size changes. So we're going to look at our closest neighbouring stars, and we came up with something called spectral class. That's a way of finding out how big a star is based on its light. And then we're also going to look at other types of stars and seeing how they move through their spectral classes and how we plot these on a Hertzsprung-Russell diagram, which we'll all cover in the next video.